Hello, everyone. My name is Oliver. I work for Wolfram Research in the numerics group, and there I work on the finite element method. So if you've used NDSolve with the finite element method, or if you've used NDEigensystem or interpolating functions on unstructured domains, or to a lesser degree, an integrate with the finite element method, you've used functionality that I've worked on. In this talk, we're going to show a multi-physics PDE modeling language that we're going to introduce into version 12.2. And I'm going to start off with a brief overview. So previously in version 12.0, we started to add PDE modeling capabilities in the sense that we've added PDE models with a background theory monograph, and then accompanying those monographs, we had a model collection in certain fields, for example, acoustics or heat transfer. And in version 12.1, we've added mass transport PDE models. And if you want to look at those, there's some recordings of the previous years where those have been presented. Let me give you a very quick glimpse on what those look like in version 12.1. So you'd have this PDE models overview page, acoustics, electromagnetics, heat transfer, and the ones that are developed have usually at least one monograph. For example, acoustics in the frequency domain. It explains a bit the equation that's been used, different aspects of that, and certain boundary conditions that are used in those in this specific field. And in this case, we have a second one in the time domain, which has a similar structure. But they also have the acoustic models, which are kind of larger notebooks that have a example or a larger example than what you'd usually find in the documentation. This acoustic mirror is presented here. It has a PDE and some code here to do the PDE modeling. In the end, you'd set up the domain, you do some meshing and some other specifications for this model. You typically need to set up initial and boundary conditions. You'd solve the PDE with NDSolve, do some post-processing, visualizations and things like that. So all of that is done in these model notebooks and in these monograph tutorials. However, as you've already seen, they've used some certain like small code blocks to do the actual PDE modeling. So this is the equation you'd wanted to model, but there was always some kind of a code involved that needed to be copied to every document that you wanted to use. And the question is a bit, could we do better than that? And so for version 12.2, we started looking at a PDE modeling language. So this is the overview we've just seen from version 12.1. And we started by thinking a bit about what are design goals for such a PDE modeling language. So the first thing, it needs to be documentable. And by that I mean, so PDEs can become very complicated. And in essence, only a full derivation of the specified PDE actually tells you what the PDE does and what the scope of the PDE is and things like that. So everything that we add, we wanted to have something like a ref page. The ease of accessibility comes to mind. So you want to be able to select some component or some term, whatnot, press F1 and get to a reference page. It needs to be easy to use. So not everyone is a PDE expert. So even for non-PDE experts, this should be usable. It needs to be extendable by customers, just simply because we won't be able to provide every PDE model that's available. So it needs to go well with what people do currently and fit in nicely into that workflow. Another design goal was that we wanted to people to see what this model generates. So you can understand what NDSolve or DSolve actually will be solving when you look at these models. Okay. So if we start looking at what are the essentials that need to go in any kind of a language that we possibly come up. So we'd always need, so if we're looking at this diffusion type of operator, we'd always need to specify the dependent variable u in this case. We'd need to always specify independent variables. Sometimes if it's time dependent, we need a time variable, so that's not present here, or we might need a frequency variable, also not present here. And very often we need material parameters like a diffusion coefficient kappa in this case. So these are essential components and some components that might come up from time to time when you do modeling. So if you've seen a previous presentation of mine, you'd know that the finite element method basically solves this type of equation. And the first thing we did is we started by generating the basic terms that this equation represents. So there's a diffusion term, this component here. There's a convection term, it's over here, a reaction term, source term, and all of these kind of terms, PDE terms, now have a reference page. So if we are going to look, and this is now version 12.2, the documentation. So you see this PDE, this diffusion PDE term has been added, detailed section, like, you know, and an example section is available. So there you go. But we're gonna look at this in a bit more detail in a second. So, and these are the basic terms that are now present. All right. So if you have such a term, for example, this diffusion PDE term, you specify the variables u, the dependent variable u of x, and x as a spatial variable as a list. So this is slightly different than what you'd specified in NDSolve, where it's specified as a sequence, but that's we'll get to that in a second. And then you specify the coefficient as a second argument. So var's coefficient is the same pattern for all PDE terms that we have. This is going to return you an inactive equation that's useful for some cases when you have nonlinear or specific Neumann boundary conditions. If you don't like this inactive version, you can always activate the inactive version and you'd get what you've probably seen from a calculus a textbook. So that's also possible. So here are a few more possible inputs. So the first thing here is now, so you can now save the variable setup in a variable vars and use it throughout all terms that you're computing. So that's an advantage, which is harder to do with a sequence. So in this case, we've added the coefficient 23. Here is a symbolic coefficient, which is a spatial variable. So now it's space dependent. Here we add u, the dependent variable, as a coefficient, so it becomes a nonlinear coefficient. And in this case, it's even a bit more complicated, where we have a spatial dependency of the coefficient. If it's in a specific region, then use this coefficient, and if it's in another region, use that coefficient. So all these sort of things are possible with these PDE terms. So how does this look like in an equation? So we have this diffusion PDE term with the variable specification and the coefficient specification. We'll set this equal to 1, and this gives an entire equation. And you can call NDSolve on this equation just normally. There's no new things needed here. So now this is the first more interesting thing. So now we can combine these terms into sums. So we have vars, we specified this here. We have the diffusion PDE term vars and the coefficient 1, -1. So you can interact in a very normal, mathematical normal way with these equations and terms to generate equations. And this is the same equation here. This time, however, we've used the diffusion term and the source PDE term to model the same thing. And again, you plug this into NDSolve in exactly the same way like you've used to do this before. Just this is a different way to generate this. Note now that this vars is used twice. So I've only specified it once, but in this entire some of PDE terms, we've used the same vars specification, which is convenient. The same is true for time-dependent terms. So we've added a time-dependent dependent variable here, plus the diffusion term equals to 1, and solve this in NDSolve in exactly the same way. So this operates nicely with all these different components. Either you specify it in a classical way, partially in a classical way, like this time-dependent component, and you generate the entire equation. And this is the major reason why these PDE terms and later the PDE components don't return equations themselves. They just return components or terms of equations, and you'll have to add them to whatever you want yourself, because then they're composable, so to speak. So you can add them together to form more complicated components. So until now, we've seen single terms and combination of single terms. A next step then is to combine those terms into larger components. So as we've seen already, this is the equation we're kind of solving. This is the coefficient form of this equation. And if you switch on and off different terms in this coefficient form, you can model various equations. So for example, the Poisson equation is made up of a diffusion term equals to a source term. A Helmholtz equation, again, is a diffusion term plus some reaction term equal to a source term. Heat equation, a time-dependent term, diffusion term, a source term. So with switching on and off these different terms, you can model larger types of equations. So what we've then done is that we've added a named partial differential equation component. So for example, we have this Helmholtz PDE component. And if we look at this in the documentation, you now see, so vars and pars, and I'll get to that in a second, is the input for all of them. Again, a details section on what it does and how it works, and examples. So when we look at this, so we have this vars is the dependent variable and the independent variable. The diffusion term vars -1 plus the source PDE term vars -1 gives this specific equation. But now we can also add this Poisson PDE component that has a parameter, which is the Poisson source term, and that gives the exact same equation. Note now the difference is because these PDE terms always get one coefficient. That, however, is not true for the PDE components, the logic components. They might have many coefficients to be specified. So then those coefficients are specified as an association in the parameters. The important thing to note, however, everything that has PDE component in its name will always get vars and parameters, and everything that has terms in its name will always get vars and a specific coefficient. Again, whatever is generated from either the terms or the components can be fed into NDSolve. Right. Right, as I said, PDE components, variables, and parameters is a typical setup of these. And here's a more specific example. So we have an acoustic PDE component where you specify P as a pressure, time, spatial variable X, T and X as a spatial variables with no parameters given will return a time-dependent acoustic model. If you don't specify any parameters, default parameters will be chosen. Yeah, so right. The next thing to look at is here is we have this frequency domain acoustic model. This is the same acoustic PDE component, just by specifying P now not as time dependent, but as a frequency dependent component, we'll get a different equation. So the acoustic PDE component is capable of delivering different types of equations for different scenarios. And that's true for all PDE components that we have, especially the physics fields related ones. Sometimes it's done by specifying a different parameter setup for the variables, and sometimes it's done via the parameters of the PDE component. So let's look at an example. So I'd like to specify a time-dependent acoustic PDE model where I specify the pressure P, T, and X, and I have a sound speed and a density. And I evaluate this. So the acoustic PDE component vars pars equal to 0 gives me the specified equation with the sound speed and density that I've chosen, and I can then evaluate that and in a normal way and have a look at what the solution of this looks like. You need to specify initial conditions, of course, but that's not unusual, of course. All right, so the PDE component is one part, but we've also added new boundary condition and boundary values, and those are there to interface the PDE that's active in the domain with the rest of the world that's outside of the domain. Everything you're going to see is going to evaluate. So what we have right now is Dirichlet condition and Neumann value and periodic condition. And everything you're going to see now is going to either evaluate to a Dirichlet condition or a Neumann value. So basically what we've done is we've looked at certain fields of physics and try to find the essential boundary conditions there, make a wrapper for them that they generate Dirichlet condition and Neumann values, which is much easier than to actually know how to set them up yourself. So we're going to have a look at this now. So if some of these boundary conditions end in the term condition, it's going to evaluate to a Dirichlet condition, and if they evaluate if they end in value, they're going to evaluate to a Neumann value. And the argument pattern is the name of the boundary condition. We specify the predicate. Where is it active? The vars and pars. And the vars and pars are exactly the same for the corresponding PDE component. So for example, an acoustic sound soft condition specified at x larger than 0 for the following variables, no parameter specified, evaluates to a Dirichlet condition. So the acoustic condition evaluates the Dirichlet condition. The acoustic absorbing value evaluates to a Neumann value. And note again in this case that the time domain has been given, and in the second case, the frequency domain has been given, and the boundary condition knows how to generate the proper Neumann value. And that's true even if you specify more parameters and things like that. Okay, so let's delete that for a second. We have the variable, again, the parameter is specified as a sound speed and the density. We evaluate this model. So we have an acoustic PDE component and an acoustic sound hard value. This is essentially the same model we've seen just now. It doesn't use 0 on the right-hand side, but it uses this acoustic sound hard value boundary condition. And with this, now you can start to do nice things, because now you can go ahead and say, for example, I don't want a sound hard value here. I want an acoustic absorbing value, for example, here. And the model is adjusted accordingly. So, and now if you evaluate this, you'll get a different behavior on the right-hand side boundary condition, because you have a different boundary condition there. So we've decoupled the equation from its components. And this means that you can also go ahead and say, for example, pars should, for example, go to material, and the material goes to tungsten. So this then also works, and this now generates you the material, the acoustic PDE that you wanted for the material tungsten. So you don't have to go around and fiddle with the equation. You just specify or change the parameters in the parameters section, and then everything will fall into place automatically. So this is a major benefit of this new technology. One other thing to keep in mind is that we can specify local versus global boundary condition parameters. So say, for example, an acoustic radiation value has additional parameters like a sound incidence pressure or sound direction vector. These can be specified in the parameters section. So I've joined the parameters density and sound speed, but you can also separate them. So you can say the third argument is the parameters, density and sound speed, and the fourth argument are these specific to this boundary condition, the specific specifications. This has, and it gives the same results. So, but this has a great advantage because if you want to specify the same boundary condition at different places with different local components, you can then do so. So where x equals is larger than 1, then we've got bars and parameters, and then the BC1 is basically the local specification for this acoustic radiation value. And the BC2 contains the local specification for this second boundary condition. So then you can combine multiple of the same boundary condition and still use the parameter setup method. Okay, so let me quickly have a quick a look at the different PDE modeling fields of physics that we have. And there, I think that the important thing is to look at, so we've discussed these basic building blocks that are now available. We've discussed the named partial differential equations a bit. We've looked a bit at these acoustics PDE components. We also have a heat transfer PDE component and a mass transport PDE component. So these are the components that generate the equations, and these are the boundary conditions that we have. And there's always a at least one monograph explaining in much more detail of what this equation does and how it's derived and things like that. What we also have is, and if you go on these, look at this one maybe. Heat transfer, that's a specific heat transfer boundary condition guide page that we have. This explains in a bit more detail what these boundary conditions do, and all of them, of course, have reference pages. You can look at them, and we've gone through great lengths in explaining what they do. So yeah, and what this page also has, this sub-guide page also has, is the specific models that we've done for the heat transfer. So for example, if we look at the shrink fitting example here, you can look at those examples. Right, so, and additionally, there is a small list of what functionality is discussed in each of these extended examples. So if you're looking for a 3D example, you might look at the joule heating or the laser welding application example. So that gives you a bit more information of where to find what if you're looking for something specific. Okay, right, so what I want to try to do in the remaining few minutes is to discuss an advanced research type of application that can be done with this. So we're going to look at catalyst deactivation. And catalyst deactivation, so you use a catalyst to increase a chemical reaction. The catalyst per se is not consumed by the reaction, but it's deactivated. In the example that I'm going to show, it's going to be deactivated by coke accumulation. So this is a gas-solid catalyst reaction. So we have a reactant G, a catalyst site S, and there's a reaction constant K1 that produces P, the product that we're interested in, and the catalyst remains unchanged. But the catalyst with time reacts with the product and accumulates coke, and it's going to be deactivated by that. So what we have here is a microscopy image of a catalyst particle. And what you see here is the catalyst site. This is the actual catalyst, and the reactant is flowing through this catalyst site and doing its thing to form the product, but at the same time is going to deactivate the catalyst. And this is done with a mass transport equation, which I've written here. So we have three species. We have the reactant, the source, and the product, and we have diffusivity for all of those. And there's a rate of mass production and consumption for all of those. So these are the reaction rates that are given for the specific concentrations, and those are plugged into the equation. Basically like this. And now to do this modeling, the only thing is what you need to do. So now we've specified 3 dependent variables. That's something I didn't speak about before, but those mass transport or the PDE components are vectorizable. So you can specify multiple dependent variables. We specify time and the spatial coordinates. And then we just specify the parameter mass diffusivity, a mass source, and this sets up the entire equation that we've written here. And then you're basically, your modeling component is basically done. What remains to be done is now to specify the domain. So we have this microscopy image, which we binarize. So we'll get a black and white image of that. And from this, we'll form a mesh. So we take this binarized image, image mesh will form a mesh. We resize the mesh to a realistic scale. And then with some image processing, we find all the catalyst sites. All the red dots are catalyst sites. And we use those to form an element mesh. So here we've generated a mesh which has 300,000 plus triangle elements. And in blue, you see all catalyst sites. So the parameters are specified. We start with an empty association. The diffusivity is specified in the solid and gas. Mass diffusivity is specified as the parameter. We move on to specify boundary conditions. So in this case, we have a mass transfer value. Again, the position where it's active, vars, parameters, a mass transfer coefficient. You specify the one you want. We specify boundary conditions. So this is a mass concentration condition. We say that for this specific component, we have a mass concentration, and that's a function that generates that, that concentration condition. Initial conditions as specified for all time-dependent problems. Then we set up the PDE, the mass transport PDE component, vars, pars, the flux, and the concentration condition, initial condition. This then is 2 million degrees of freedom, so it's a large-scale problem. We stuck this, put this into NDSolve. It will compute the reactant functions of those. Takes 1,100 seconds to compute, a little more than 11 gigabytes of memory required. And then we'll have the catalyst down here, how it changes over time, the concentration in mole per cubic meter, the product and the reactant. And from that, we can still compute the coke accumulation by doing this equation again. So we multiply these two components, so with the reactant equation and time integrate over it, and then you'll see how much coke has been accumulated in this microscopy generated image in 5 seconds. Yes, so I think my time is almost up. So I thank you very much for your attention. The modeling guide and the models overview are probably the most two essential components for starting your modeling career, if you will, with the Wolfram language. That will give you an overview or starting points for doing so. One last thing I'd like to mention is that later today there is a finite elements meetup. So if you are into finite elements and things like that, you're most welcome to join me later today. That's it from my side, from my part, sorry. I'll discuss questions that you probably will have for this in the meetup for the finite elements. I think we'll have a bit more time to do this over there then, yeah? So hope to see you later and enjoy the conference. Bye for now.